Welcome back to another episode of Data Science at Home podcast. I'm Francesco, podcasting from the office of Amethyx Technologies based in Brussels City, Belgium. Now, we all know that the human brain is indeed a powerhouse that can host something like 90 billion or something neurons. Uh, and it can use up to, I don't know, probably 15, 20 watts of power. So it's an extremely efficient machine, if you think, right? Now, there is, of course, this is not the current situation with, especially with large language models. We have seen and we have heard of some of these gigafactories that are going to be built in the very near future. And I actually ended up on a website that looks and sounds really, really sci fi. The website is finalspark.com. And today I'm with the co CEO of FinalSpark, Fred Jordan. Hi, Fred. How are you doing today?
Fine, thank you. And I'm happy to talk with you today.
It's a pleasure because what you guys are building at Final Spark is really something that sounds sci-fi. So it would be very nice to clarify with you first of all what you are building, what's the vision of Final Spark, because Final Spark, for what I can tell, is a company that wants to build bioprocessors or biological things, right?
Yes, yes. And well, basically, you said everything at this point.
Oops.
I have nothing else to add. So, yeah, you're right. The idea here is digital processors using transistors, right, to do logic gates for computation. And here we tried to really revolutionize the whole field by saying, okay, we are going to try to build the first processor where we replace these transistors with living neurons. And
Mhm.
as you said, how I mean, it's quite an obvious statement to say, well, we have energy problem with digital processors, and as you mentioned, neurons are very power efficient. So why not use them?
Right. Well, yes, indeed. Also, because the human brain works since several thousands of years. So, why not continuing that? It's indeed a great vision. Now, of course, there are many, I believe, many challenges and many limitations of all this. And also, and that's exactly what I would like to clarify with you in this episode. I guess my first question is, can you walk us through what happens from the moment you, let's say, extract neurons to when they are actually performing computation? For example, what does a training cycle look like for a biological processor?
It looks like something which is not very much working at this point, I must say. Okay, because the training, you really nailed it to the important thing here is training, and this is the main challenge that we have in this field of biocomputing or wetware computing is to train those neurons, or more precisely the network of neurons, in order to achieve something useful. And it's very interesting because it's exactly the same situation that it was 30 years ago with artificial neurons. People didn't know how to train them.
Mm.
Okay. And then we invented some algorithms, and then we have AI today. And now we have the same problem here with biological neurons. But the good news is we know it's possible to train a biological network of neurons. We know it for sure because we are able to learn ourselves. So we know at the core of this network, there are some mechanisms which are built in for learning. So all we are trying to achieve is to reproduce what works in vivo in our brain, in vitro in our lab.
Right. And the fact that we humans are like a living proof of the fact that indeed we can learn. Obviously, it took us several millions of years. Now, if we follow the laws of evolution, now I don't want to get there because I personally don't have those, I'm not technically prepared to discuss these things. But I guess my question is, uh, how does this happen? How do you see this transition happening from silicon to bioprocessors, or a term that you used, it was wetware computing, or
Yeah, Wetware computer or organoid intelligence are some of the words which are used. So the transition, I guess, it's going to be fundamentally a bit similar to what we've seen with artificial neurons. Okay, um, 35 years ago, it was all about doing XOR gate. Okay, so very basic Boolean um, gates functions using artificial neurons. Okay,
Mhm.
and then from this it evolved until the point where we have ChatGPT, right? So this is exactly what we are trying to do right now. Okay, is to really do some basic tasks like storing one bit of information or changing how much they spike or when they spike. And at the end of the day, what we want to have is very similar to what you have with artificial neurons. That means we give an input. This can be, I don't know, an image of a cat, and it outputs it's a cat.
Right. Okay. So in terms of the applications, in fact, the vision is to, let's say, reach potentially what we can already do with silicon, but of course, doing that with a bioprocessor, it would be ideally a million times more efficient than than burning electricity as we do now with large language models. So that's indeed a very super cool vision. I mean, a super cool benefit for sure. I guess my question is, silicon is much easier to, it's much easier to reach high level of reproducibility, right? That's as you said, logical ports and Boolean algebra. It's there. It's something that you keep repeating, regardless of the years, regardless of the conditions. And probably this is not exactly the same for bioprocessors. So how would you handle reproducibility in the second case?
Well, you also, again, it's exactly the important point here is the intrinsic variability of life. Okay. And here we are working with living cells that connect, I would say, freely together. Okay. And each time we create what we call a brain organoid, which is a collection of neurons connected together, which creates a small nervous tissue, we get a different individual, I would say. So
Mm,
they are all different. Okay.
wow.
So there are several ways to mitigate this. On the biological side, we have protocols that try to increase the reproducibility of what we get. Okay, on the biology side, but there is also on the algorithmic side, the way we interact with those neurons. We have algorithms that start when we have a new brain organoid. We start by running algorithms to discover what do we have here today. Okay, basically. So we are going to scan all the electrodes and to adapt. Okay, so we can have adaptive algorithms to compensate for the natural variability.
I see. So you're saying that these bio machines, I don't know, I'm just forging a terminology here, um, can have their own some kind of personality, quote unquote.
Well, personality is really a big word. Consider that right now, our typical brain organoid have a collection of about 10,000 neurons, okay, which is
Mm,
less than a fly, okay? So I'm
okay.
not sure about the personality of a fly, okay? But at least they are going to have a different way to react to stimulation and to have a different spontaneous activity. We see this every day, and we can adapt.
Right. So this brings me to the fact that, for example, it's just my personal observation. When you, let's say, productize this on or scale this approach, you might also be selecting, the let's say bioprocessors that perform the best under certain conditions or more robust to certain type of algorithms, right?
Yes, so in this direction, there are different ways to go. For instance, in your brain, there is not one type of neuron. There are about 400 types and subtypes of neurons. Okay,
Mm.
so for different area of the brain, we can create different brain organoids. Okay, So it starts there. Which type of neurons do we want to create? And this, we select this during the differentiation process with specific molecule that we can introduce in order to force the neurons to be of this hippocampal type, of striatum types, or cortical types. Okay, so that at least this is one way to direct which type of neuron.
I see. So this, I mean, this complicates the, the scene a lot more, because when we think about, for example, I would call it traditional AI at this point, or classic AI,
Yeah.
like there is only one single type of neuron, with a, that mimics essentially, the firing mechanism of a neuron with a function, a mathematical function, in fact. Uh, well, here we are saying, okay, since we are dealing with a bioorganism, well, guess what? Bioorganisms have a lot more types, so we're gonna deal with that as well, which is, I find it absolutely, I mean, I would say crazy, but in a good way.
Yeah, but you have to consider something else, okay, which is very funny. Okay, you were saying, oh, microprocessors, you Fred, microprocessors are all the same, and we because we master, okay, the way it's done. But that's not correct. Okay, when you buy a microprocessor which is validated at 10 gigahertz frequency, for instance, what happens at the production site is that they test it. Okay, and if it doesn't work at 10 gigahertz and it works at 1 gigahertz, they will label it at 1 gigahertz. So even for the most control process like microelectronic, we still have intrinsic variability. So I
Right.
think it's the reality. When you are at the edge, you have variability and you can cope with it.
Yes, we just don't realize it. Like, we consumers who buy a CPU, we think that when we buy an AMD, Ryzen, whatever, they all gonna be the same, but actually not, because indeed at the micro level test, they responded differently,
Yes.
because we are at the atom level almost. Wow. Okay, so much stuff. Well, this is a very controversial topic, and I'm pretty sure that the listeners of this show will find this a bit weird as an episode, but I find extremely interesting, because things are changing so fast, especially in AI, that of course, considering bioprocessors, it's in my head, it's like the next step, the next logical step. Uh, Rather than increasing the size and the dimensions of these models ad infinitum, which I don't find it interesting anymore, personally. um, Fred, I think we should cover a bit about energy, because here it's like, I'm a super critical person, so don't get offended with my questions. Which is the following. So when we calculate energy efficiency, we calculate it at the neuron level, but in fact there is a lot more that you spend in terms of energy before you get there. I don't know, I'm just guessing. I believe there is a bioreactor or something in your labs, or whatever is the equipment, and please feel free to expand on this if you need. uh, Temperature control, I believe, whatever. All these things all together, they spend energy. So what would be the efficiency when you consider the entire system, also the production one?
Yes, it's a very good remark, actually. And as Professor Artung published 2 years ago a review when it tried to make an evaluation of the energy efficiency difference between artificial and natural neurons. And he came out with this number that you already cited, which is 1 million times more efficient. Okay. But you're right that there is the difference between this and actually a functional biocomputer. In our projections, we consider that the actual gain of efficiency would be about 100 to 1000. Okay, so we just put it directly 1000 of losses in the system, and many things, including the difference of speed of processing of the biological neurons. So with this we feel comfortable to say this when you start with 1 million, okay, you have some room
Oh, yeah.
for losses here and there.
Interesting. And if you wanted to make some comparisons, if possible, of course, to make the episode more approachable for non-technical people, what would be the current state of the art, or, well, what have you reached so far if you can compare that to, I don't know, an old processor that we probably know, um, what would be that comparison? And I guess my continuation of the question is, what can I actually do? What can I currently do with, I believe, 10,000 neurons, biological neurons?
Right now, I would say close to nothing. All right.
Okay,
So,
that's a good start.
so if you want to compare with a processor, any type of processor is already more useful than what we have at the current stage. Right. So let's put things in perspective. We are closer to what we were at the beginning of the invention of the transistors when the first gates were built. Okay.
Mm,
So the things that we can do maybe is store one bit of information, or change the way the neurons react to stimulations, or the way they spike over time, so we can influence their behavior and their response to stimulation, which is already good, but it's clearly not enough yet to have a functional processor.
sure. I see a very close analogy to what's happening in quantum computing, for example, where the
Mm.
number of qubits, of course, is a lot smaller than what we expect and what we are used to. And I believe that, as we go, of course, this is part of the typical evolutional trend. We will get better. We will get to scale these things. If the idea is sound, uh, for sure, it's just a matter of time. Um, so that's a very good analogy that I found by reading a bit of the documentation, whatever I could find about FinalSpark. Um, I have actually a question about aging because I believe that also traditional microcontrollers or processors, they will age in the sense that some uh, transistors will just stop working because of uh, power drain or electricity, spurious signals and stuff like that. Is that a case for bioprocessors as well?
Well, yes, they are aging also. But your neurons in your brain basically are designed to live about 1 century, because you are going to live all your life basically with the same neurons.
Mm,
Okay, that don't, I would say, schematically they don't renew. Okay, there are a few stem cells, but this is anecdotic, right? So 100 years is already quite good, actually. And there are some self-healing systems, I would say, in place around neurons, which are the glial cells in particular, which take care of the health of the neurons. You don't get them in digital transistors. Okay, and
right.
when you have a digital transistors, actually you have gradient of concentration of doping materials like arsenic and aluminium, for instance, which are going to be dispersed in the silicon as time goes by, and at what point it will not work anymore, and it will never come back again to life.
Wow. So, okay. Now, this is probably will sound like a very stupid question or a very popular one. Like, imagine I go to a shop and I have to buy a bioprocessor. How does it look like? What do I bring home? That's a vision, of course. Like, I bring back some kind of organic thing, or how does it look like?
Um,
How
so
would
today,
it look like?
a bioprocessor really looks a bit like in the 60s, like you need actually a room, you need a full lab, okay? Because I can give you parts of this. I can give you the electrodes, for instance, but that's not enough. Of course, you need the neurons, okay? But
Right.
I cannot give you the neurons like this. I have at least to put them in the tube, okay, where they can live maybe 48 hours. Then they have to be transferred in conditions where they can keep on living. And then you have to transfer these brain organoids on the electrodes and in a special environment to make sure they live in the long time. So it's not a situation when you could buy this ready to be used. It's we are far from there.
Okay. No, makes sense. I mean, I was not about to go to any shop and ask for a bioprocessor.
But that's funny because we have also some universities around the world that sometimes send us some brain organoid that they did. Okay, they send us by post. Okay, so
Okay.
sometimes it takes 2 days, and we keep them here, and we can measure them, and they see in remote the activity of their own neurons. So we also ourselves send some brain organoids to other universities. So they travel. It's okay, but you need to have the necessary hardware to have a good receipt.
Right. Yeah, makes sense. Okay. Um, Fred, I think that my next question is about, again, in the happy path that the technology works and it's scalable. Scalable, not necessarily. It's like it works on under certain constraint of reliability and reproducibility, of course. Which type of tasks do you think that bioprocessors would excel at? Because, for example, we humans, with respect to machines, we will never be as good as machines to, calculate the square root of trillion something, right?
Yes, you're right. I think it's a good example. Okay, I'm not going to use a biocomputer to do computation. That would be really a pity. Actually, you have to take the things in reverse order. Okay, when we talk about AI today, AI is working with simulations of neurons.
Hmm.
Okay, all AI system, well, not all. Okay, most of the systems that we know about, like ChatGPT, works with simulation of neurons. So the first application would be obviously to replace these digital computers that are running simulations of neurons with actual neurons. Okay,
Right.
and then the applications are way more obvious. It's going to be like all generative AI applications, like ChatGPT, for instance. Okay, you could have it theoretically, of course, running on a biological computer. It's perfect. So running Windows 11 on a biocomputer is a very bad idea. But ChatGPT is okay. Image recognition also. Now you have really, I think, also to focus on tasks which are the same time level, I would say, as us human beings. Okay,
Right.
we are discussing together right now. Compared to computers, it's incredibly slow, and
Yeah,
and the reason behind it is that the action potential of our neurons stays for about 2 milliseconds. Okay, this is the limit. Okay, that we have. Okay, so the applications are going to be in AI when typically you have interactions with human beings. That's just perfect.
I see. So, like what? Like still pattern recognition, anomaly detection would that still be something that biological neurons can do?
Yes, well, they can do it. Okay, but I would not bet that that's the top because of the speed. Because if I take an NVIDIA card, I can do I know 1 million recognitions per second, things like this, and we have a problem here with neurons on the speed side. Okay,
Mm,
now for conversations like the one we have right now, it's just perfect.
right. So wherever there is a human involved, and of course the time uh, scale changes with respect to a computer, of course, that makes sense. Okay. Fred, I think that this type of projects would raise a lot of eyebrows in the ethical department because, I believe there has been some philosophical questions that they've asked you. Uh, if you want to share something, some of them with us, that would be clear. That would be great.
Well, the things about ethics and philosophy in general, okay, is that I'm not competent in this field. Okay, I'm a scientist. Okay, but it doesn't qualify me in any way for any reason to talk about ethics and philosophy. It doesn't mean that it's not important. I think it's very important. So what we decided to do is to try to liaise with a number of academics who are working in the field of philosophy. There are people who spend their whole life. These people are qualified. Okay, so what I can do is to bring them the science that we do, and then they do their things. Okay, based on their culture and all their expertise. So this is what we are trying to accomplish.
Right. Well, of course, I'm no expert here either, but whenever you put in the mix something that is organic and there's biology involved, of course, even a scientist should start raising an eyebrow, say, okay, uh, what can happen with this thing can run out of control. I mean, they're already raising these questions with, for example, large language models, which I personally don't believe they're gonna have some form of reasoning or some form of, I don't know, wisdom, or they can be dangerous for human beings, or kill us all. I don't believe that. Yeah. When the thing is biological, though, probably it's because it's closer to us as humans, and that makes us think in a different way. That's probably the. I guess my question to you is that, is there any unexpected behavior that you have observed in the lab so far?
There are a lot of unexpected behavior, okay, and it boils down to variability. Um, it's, when you stimulate neurons, you never know really how they are going to react, okay,
Mm.
and that's part of the game, okay. And what we want here is actually to control this, to change this random behavior, to guide it to have a useful behavior. And at the end of the day, it's really exactly mathematically it's the same problem as with AI and artificial neural networks. What you want is that for a given input, you get the expected output. And there is one way to do this is just to adjust the synaptic connections between the neurons. Okay, so
Right.
when we create a brain organoid, okay, we have thousands of neurons connected randomly. They are going to have a random output. But if we rewire them, then we are going to have a useful output. So this is only what we are trying to accomplish here.
Wow. It's like steering nature to your objective, in fact.
Well, yeah, but it's not different to what you're already doing yourself with your own brain. Okay,
Sure.
when you learn something, you are rewiring your neurons to know the things. So we are just trying to reproduce something which already exists.
Yeah.
And actually, we want to rely on the learning mechanisms which already exist in our brain. We are not going to change the synaptic weights directly ourselves as we do in AI. We are going to rely on, for instance, on reward mechanisms in order to let the systems rewire itself in order to accomplish its task.
Oh, wow. What would be a type of reward in such cases?
Haha, this is also, you have very good questions actually. Only fundamental, just to the point, the right questions. So the reward is probably one of the biggest mystery of learning, okay? And I'm going to tell you, there is not so much answers to this, okay. As far as I know, there are only two answers, okay, two types of rewards that we can produce in vitro today, okay. I may be wrong, but these are all I know, okay. So the first reward are chemical rewards we can produce with the dopamine system, for instance. So dopamine is one of the neuromodulators which are implied in the learning process. Okay, and this is one thing that we use actually in our own lab. We have dopamine release systems that are meant to, let's say, reward the brain organoids when it does what we want. Okay, it's very
Right.
similar to give a treat to a dog if you want. Okay,
Positive reward. Yeah.
yeah. And there is another type of reward which is not chemical, which is purely electrical, okay, by stimulation. So this one is called the free energy principle of Professor Friston, okay, which states that biological systems seek predictability. Okay.
Mm.
Therefore, if you stimulate regularly with a frequency which is always the same, some neurons, they are going to have a predictable input, which they are supposed to like. So that would be perceived as a reward. On the contrary, if you stimulate randomly, this is going to be an unpredictable input that may be considered by biological systems as a punishment. Okay.
Right.
So, and these are the all things I know about reward and punishment that exist right now in biocomputing.
I see. Which are in fact very similar to, I mean, in fact, we copied from silicon reinforcement learning reward functions, engineered reward functions that essentially mimic the way, that's what a behavioral type of reward. But here we are at a much lower level, which is biological type of reward or chemical reward, which is incredibly
Yeah,
interesting.
it's incredibly fascinating that for 30 years we've been trying to mimic
Yeah,
digitally neurons, and now we are
never
coming
got the
back to the sources. Okay, let's use the real thing. That's very
opportunity.
funny. Okay.
Is I find it fascinating indeed. It is going back to the origin, in fact, to the primordial situation of biology. Fred, I can stay here and talk to you for another couple of hours, but I unfortunately cannot do that. So I'm gonna go straight to the my last question. Actually, my last two. This is a heavily, as we all understand here, this is like super research, how we can call it, uh, super experimental. Now, how does the financing work in this particular for this particular company? Because how do you convince people to fund a project like this one? uh, and I'm personally curious about this very question, because it's very cutting edge. It's like, as I said, sci-fi.
Yes, it's sci-fi, and also it's also why I love it. By the way, because I love sci-fi. So,
Oh, we too.
so how do you finance this? Okay, there is. I tell you how we do it. Okay, so this is my second company, right? I have another company that I co-created with a colleague, which is called Alp Vision. And this company, we made it after our PhD 25 years ago. It's very profitable,
Mm,
okay, and we own it 100%. So we use actually the profits of this first company to invest into FinalSpark because, as you said, this is so deep tech, okay, so out of all the standards that it's extremely difficult to have a venture capitalist bet on these kind of things. I think the only way to get financing here would be sovereign funds. So this is also what we are looking at.
I see. So for sure, we're gonna share some of the contacts in the show notes of this episode on the official website, datascienceathome.com. But before we say goodbye, or arrivederci, as they say in Italy, which means see you later. um, as you said, it's very difficult to find finding for this type of projects, especially now that there is this like frenzy about large language models and almost AGI every year. It's like they keep saying that. I would like to ask you, what do you think about the current state of artificial intelligence, as a personal opinion? Of course, if you want to share with us your personal opinion.
Well, I must say something very important on this point is that we started actually to use LLM for making experiments with neurons.
Mm,
So I don't know if you get what it means. Is that for the past few years we've been working as researchers, like every scientist in the world in any
right.
field, okay, uh, designing experiments, running experiments, understanding the result, and designing the next experiment. Okay, right. Since a few weeks, we started to let a ChatGPT do this for us.
Mm,
Okay,
interesting.
so that means we are in the process to give our ChatGPT the way to work as an agent. So now it's an agent, okay, LLM, the power to actually directly stimulate neurons and explain what it's doing, get the inputs from the neurons, interpret this, and explain to us what it concludes and what's going to be the next experiment. And if it does this every 10 minutes, and we have a reports every 10 minutes. And I can say we are totally amazed by the experiments it's doing. I mean, we have some experience in this field. I would say, unfortunately, because it takes some time, and so we can really appreciate the ideas that he puts in practice and the conclusion it draws from this. It really makes a lot of sense. So here, AI is going to accelerate tremendously the venue of these new biological computers.
I totally agree. Indeed, AI in certain domains, especially when they are quite narrow, because in this case you're automating tasks, or you're automating experiments. In fact, with AI as a tool, that indeed it has already proven to speed up things pretty much in several sectors for sure.
Yes, because you have to realize that in our case, we are writing Python script to design algorithms in order to find the right stimulations to perform training. Okay.
Mhm.
But ultimately, what we envision to do in the following months is to give the ability to ChatGPT to write itself entirely the Python script.
Right.
So it will do the programming for us entirely and the understanding of the experiments and everything.
Yeah. How big are these code snippets usually? Like, are they super complex? Are they super modular? Or is it one script of, I don't know, 100 lines of code for Python?
No, they can be very, very good, and they can take indeed several hundreds of lines sometimes. So right now they are offline. Okay, we let ChatGPT agent only interact through reduced API. So
Mm.
we try to control what he's doing, not killing the neurons. But we know because we've done other experiments that he can come up with hundreds of lines, which makes a lot of sense, and that we have executed in simulations before, and we are confident that we'll be able to give him full power.
Nice. Well, I would be very happy to, get in touch again, if you, hopefully as soon as possible. But of course, I believe there is some time before we can see some, tangible results with this. I will still keep an eye on finalspark.com. Fred, this was great. It was nice to have you here on this show.
It was a pleasure, and I really loved your questions.
Thank you so much. And of course, as I said, we're going to share some of the very important links. Finalspark.com is, of course, one of them. That's the official website. And then, of course, there are some interesting blog posts. And I also found a very interesting video on YouTube. There's more than one. We're going to report some on the official website at datascienceatom.com.
You have also the Discord server of FinalSpark, when people can come and ask questions, and we try to answer to every questions coming from everyone. So
That's great. That's great. Okay, Fred, this was great. And thank you. Thank you so much again.
thanks, pleasure.